Let's launch into the second part of our lecture on minerals and discuss several classes of minerals that we will see. And then we're going to focus on the silicates because they end up being so common and important in Earth's crust and mantle. So here are the important classes of minerals. You'll see at least one example of each of these in your lab. And these are relatively common classes of minerals. And it's not an exhaustive list. There are other types of minerals as well. But we tend to classify minerals based on the anionic units that make them up, just because there are so many different metals that make cations that can end up in minerals. We tend to classify them instead based on only the few types of anions that can end up in minerals. So silicates are made partially of silicon and oxygen in those silicate tetrahedra that we already saw. Carbonates are a type of mineral that has carbon bound to oxygen in these triangle shapes. This is not complex enough for us to call carbonates organic because the only bonds carbon has is to oxygen. So it's pretty simple. Native elements, that means that it only has the element itself and there are no anions or cations in it. These are often metals. So you might actually find natural native copper that's made only of copper atoms, or you might find natural native silver or gold if you get really lucky. There are also sulfides that have as part of them the sulfur anion. And then there are oxides that only have oxygen as their anionic component, but they don't have carbon bound as carbonates, and they don't have silicon to make silicates. So these oxygens are another class of mineral. Now, if we want to think about which ones are most common, silicates make up most of our igneous rocks. They make up most of our metamorphic rocks. And they also make up a big component of sedimentary rocks that break down products at Earth's surface. A lot of other minerals weather away fast enough that we're left with mostly silicates in those rocks. Not only, but a large part of them. Another big contributor, but not nearly as big as silicates, are carbonates. They make up limestone, which is a sedimentary rock that's very common in Tennessee and a lot of places on Earth's surface. And related rocks, like rocks that form from limestone when it metamorphoses. But we're going to focus on silicates just because they make up so many different types of rocks. So they deserve special focus just because there's so much of them. They're built on the silicate tetrahedra. We'll write that sometimes as SiO4, and it turns out it has a total 4- charge. Even though it's multiple atoms, we sort of treat it as its own anion because the bonds between each of these atoms are these strong covalent bonds, so they tend to stick together. The whole thing has a -4 charge. Sometimes I may leave that off and just write it as SiO4. But whenever you see a silicate tetrahedron, you should think that on its own, with nothing else connected to it, it's going to have a negative charge. Many silicate minerals are going to have other metals to balance this out. They'll have other metals like iron with a positive charge. So cations of iron, sometimes there'll be 2+. You might have magnesium in there. You might have aluminum. You might have calcium. You might have sodium or potassium. These are some of the most common other metals that end up bound to these silicate minerals. And they are bound in a form where they have positive charge, where they are cations, to balance out the negative charge. Why is it? Why do we have so many silicate minerals at Earth's surface? This is just a table of the composition of Earth's crust. So remember, that's that outer skin defined as being made of silicate minerals of a particular type. And it forms the entire outer skin of Earth. And if we look at the percentage of minerals in Earth's, or the percentage of just the atoms, excuse me, that end up in Earth's crust, we'll see that almost half of those atoms are oxygen. And then more than half of what's remaining is silicon. We have so much silicon and oxygen at Earth's surface that they can't help but combine into silicate minerals. Then there are other things as well. There's a little bit of aluminum, iron, and magnesium. But compared to silicon and oxygen, they're a relatively minor part, so that most of our minerals end up being made mostly of silicon and oxygen. They make silicate minerals. We talked about this a little bit. The silicate tetrahedron, which the plural is tetrahedra, they're negatively charged. The silicon itself has a +4 charge, and each oxygen has a -2 charge. But all told, overall, that total charge is -4. Now, to build a mineral, that charge must be 0. It must be neutral, because like charges repel and opposites attract. So if we had a net charge on it, the mineral would try to push itself apart. So that means to this structure, we can do two things. We could either add positively charged metal cations, or we could start to stick these tetrahedra together in what's called polymerization, which essentially removes one of those oxygens. By sharing one oxygen, they can get rid of one of those other oxygens and remove that negative charge. That's how you end up balancing charge in these minerals. And we'll talk more about that in lab as well. So what is polymerization? What do we mean by that? Well, it's sticking together. Polymers are types of chemicals that are made of individual units called monomers stuck together in a regular pattern. In the case of silicate minerals, the monomer is this tetrahedron, this silicate tetrahedron. And when they stick together, they end up sharing those oxygens like we saw. So if I diagram two cases in sort of 2 dimensions, where we imagine one of these is silicon with oxygens at the corners. And I'm just drawing it in 2D to make it easier for myself and easier to think about. If these aren't connected to one another, they're not polymerized. We don't see any bonds between the tetrahedra. But we could come up with a structure where they do share their corners. Because these tetrahedra are now connected to one another at some of their corners, we call this structure polymerized. Because the monomers, the tetrahedra that make it up, are connected to one another. There are many different ways that you can end up with polymerization in silicate minerals, and it's going to be important to learn about. So here are some examples. In the mineral olivine, the tetrahedra are not bonded to one another. They're isolated, like that last picture that we looked at, like this structure. In pyroxenes, they're connected into single chains, much like the structure that we drew before. A chain in sort of one dimension of tetrahedra connected to one another. In amphiboles, they're connected in double chains that are double wide. In MICAs, as we saw before, they're connected into sheets. In FELDSPARs, we'll see they're connected into a 3-dimensional framework. Be on the lookout for another video where I talk about that in depth for each of these minerals, and I show you the structures a little more carefully. You'll also see those in lab. In addition to the polymerization state, we can classify minerals as either mafic or felsic. So here are some new vocab words for you. Mafic minerals are those that have relatively few silicate tetrahedra, and they have more metals in response, high magnesium and iron, sometimes 2+, sometimes 3+. Mafic minerals tend to be dense. They tend to have a dark color, and they tend to weather fast. So if you find a silicate mineral that is dense, has a dark color, or weathers fast, that's the observation that you would make. Your interpretation would be that it likely has a high content of magnesium and iron, and that we would classify it as a mafic mineral. So that's what mafic means. Felsic, in contrast, has a lot of silicate tetrahedra and low amounts of magnesium and iron. These are less dense, they're lighter in color, often white, gray, or pink, and they weather relatively slowly, at least compared to the mafic minerals. Okay, so let's think about the properties of mafic versus felsic and why that's the case. So the density. Silicon is lighter than other metals. Magnesium and iron tend to be heavier than silicon. So having a low amount of silicon and high magnesium and iron increases the density. Which type of mineral had a lot of magnesium and iron? The mafic silicates have a lot of magnesium and iron, so they're going to be more dense. So let's think back to what we learned during the plate tectonics lectures about the density of continental and oceanic crust, because we can use that to remember which type of crust is made of which type of minerals. Both types of crust are mostly made of silicate minerals, right? The crust is mostly silicates. One of these types is mostly mafic minerals, and one of these types is only felsic. So take your guess, which is made of which. And then we'll see how we can remember. So the continental crust is floating above the oceanic crust. Both of those are floating on the mantle. Why is that? Why do we have continental crust and then oceanic crust is sort of lower, and then the oceans sit on top of it? Because the oceanic crust is sitting so much lower. Why is that? Well, it's because the continental crust is lower density, 2.8 grams per cubic centimeter. Oceanic crust is more dense. I believe this was about 3.4. So the silicate minerals are the least dense in continental crust, in between for the oceanic crust, and the most dense for the mantle. Which type of mineral was less dense? These are felsic silicates. These are mafic silicates for the most part. And these are even more mafic. The mantle is the most mafic. We call it ultramafic. It's so mafic. Talk about that later. But remember this, continental crust, less dense, felsic silicates. Oceanic crust, more dense, mafic silicates. Okay, let's talk about the other properties. So for silicate minerals and their color, magnesium and iron, for processes that you'd only learn about in like physical chemistry classes, they tend to absorb more light. As a result, they're going to look darker in color. Therefore, mafic minerals with a lot of magnesium and iron in them are darker in color. They tend to be black, or sometimes they can take on a green color. And that green might even be moderately colored or slightly lighter. But the point is that this black and green color comes from the magnesium and iron absorbing light. So if we look at felsic rocks, which consist of mostly felsic minerals, like these, they tend to be lighter in color. And the mafic minerals tend to be darker in color. So the mafic minerals end up in these mafic rocks. Continental crust is made largely of felsic rocks, which in turn are made of felsic minerals. Oceanic crust is made of mafic minerals, or excuse me, oceanic crust is made of mafic rocks, and those rocks are made of mafic minerals. Intermediate rocks have both mafic and felsic minerals in them. And so they end up having an intermediate color. We'll see more about that in the igneous rocks lecture. Let's talk about weathering. Weathering, once again, is breakdown at Earth's surface. Often it's due to the action of wind or water, especially. Water does a lot of weathering at Earth's surface, especially chemical weathering, chemical breakdown of minerals. So when these silicate tetrahedra polymerize, connect to one another, they do so with strong covalent bonds that we draw as sticks. Because it's mostly strong bonds connecting them together, they are much harder to break down. They're much harder to weather, much more difficult to weather. As a result, felsic minerals tend to weather more slowly. If you start with some felsic and some mafic minerals and leave them at Earth's surface, the mafic minerals will weather away and disappear much faster than the felsic minerals. And pretty soon, you'll be left with only felsic minerals at Earth's surface. Okay, now let's talk about the 8 minerals that are silicates that we're going to have you identify in lab. I'm going to show you them each once, and I'll talk about each of them once in here so that you have a starting point to start to think about these. So olivine, what do you see? What color is it? It's green. It's almost always going to have this green color, somewhere in between this light green, this dark, and this olive green. Those are the colors that you can expect olivine to be. It's made of isolated, non-polymerized silicate tetrahedra. There are lots of magnesium and iron ions in there to balance the charge, and it doesn't have a lot of very strong silicon-oxygen bonds, so it weathers pretty fast. This is a mafic mineral, as we could tell based on the green color. Green color is our observation, interpretation is mafic. Augite, it's a type of pyroxene. Pyroxene is a class of minerals, and augite are these black minerals in here that have a sort of square to rectangular profile. They tend to be greenish black in color. They have two cleavage planes at 90 degrees. And if we put two things at 90 degrees to one another, what do you end up with? Square or rectangular shapes. They're dense because they have a lot of magnesium and iron. They weather pretty fast. They're mafic. They are made of single chains of silicate tetrahedra. All pyroxenes are made of these single chains. And here we see one of those chains. And here we see one of those chains. If you want to see how the triangles that I drew before match up with this, there are those triangles. Or you can draw the tetrahedra if you want to think in 3 dimensions. So that's pyroxenes. And in particular, one type that we talk about is augite. Hornblende is a type of amphibole. Hornblende is the name of the mineral. Amphibole is the class of silicates. These are made of double chains of silicate tetrahedra. So if we look carefully here, one double chain, and the chain continues in this direction. But this double chain here does not connect with this double chain here, which are linked, does not connect with this double chain here, which are linked. So double chains, it has a substantial amount still of magnesium and iron in it, so it is going to be a mafic mineral, but it does often appear in felsic rocks as just the little bit of mafic stuff in those felsic rocks. Hornblende is black. It has two cleavages at 60 and 120 degrees, as we see here. So sometimes if you get a really good sample, it will be diamond shaped. It also weathers fast because it's mafic. Biotite is a type of mica. Mica are sort of in between. They do have a lot of silicate, but depending on which type of mica it is, it could be mafic or felsic. Biotite, can you guess which one it is? This is the mafic one. It's dark in color. So it's dark brown to black because of the magnesium and iron in the structure. And these here, that's where the magnesium and iron are, just to point that out. It peels into these thin sheets and it weathers relatively fast. Again, it's mafic, but sometimes it'll appear in felsic rocks as just little specks of black in there. If you have a granite countertop, some of it might be biotite that makes those little dark specks. Some of it might be hornblende, that amphibole that we saw before. These are made of sheets of tetrahedra. So all of these tetrahedra here are connected to one another in a two-dimensional sheet shape. Kind of like you took those double chains of amphibole and jammed them all together, you would get a sheet shape here, right? It's 2 dimensions, connects that way, but it doesn't connect up and down out of the plane. That's why we call it a 2D sheet. Muscovite is also made of these sheets. It's also a type of mica, but it's much lighter in color, light brown to white, even colorless. No magnesium and iron in this mineral. It peels into thin sheets. It weathers moderately slowly, but still it has these weak ionic bonds, so it weathers faster than some other minerals, but it weathers slower than the mafic ones. This one's felsic, and we can tell based on the color. Just like biotite, it's made of sheets of silicate tetrahedra. Now we're into the feldspars. We'll talk about 2 types of feldspars in here. One is potassium feldspar. I might call it K-SPAR because K is the elemental symbol for potassium. You might also call it orthoclase feldspar. It's got this light pink color oftentimes, sort of salmon pink, and it tends to make rectangular prisms with sort of irregular ends to them. But this side's a rectangle and this side's a rectangle. And then the third side is a little irregular. Pink, sometimes other light colors, but really if you see a pink rectangle, it's probably potassium feldspar, at least in this intro class. It's got those two cleavage planes to make the rectangular prisms. It's also pretty hard. That's what I mean here. It can scratch glass. It weathers pretty slowly because it is a network of tetrahedra connected to one another. Oh man, this is complicated, right? It's connected in all directions. This one's connected to that one here, that one here. They're all connected in 3 dimensions. And there are just a few other potassium ions thrown in. Because it's connected in all directions, it's relatively hard and it weathers slowly. It's a felsic mineral. Okay, sodium feldspar is the other type. Once again, it makes rectangular prisms. There's a nice regular cleavage face. There's a nice regular cleavage face. But then the third face is a little bumpy and irregular. Same idea as with orthoclase or potassium feldspar or K-SPAR. Sodium feldspar, aka plagioclase, it's lighter in color, tends to be white to light gray. 2 cleavages can scratch glass, forms rectangular prisms, weathers slowly because once again, these are all connected to one another. And instead of potassium now, these ions are sodium and a little bit of calcium substituted in sometimes. But right, we're calling it sodium feldspar, so most of that's going to be sodium. This is felsic. It appears in both felsic and mafic rocks. The last one, and we've talked somewhat about this already, is the mineral quartz. Quartz, it can scratch glass. It's harder than glass. It's harder than all the other silicate minerals we looked at. So far, the only mineral we've seen that's harder than quartz is diamond. And we won't talk about any others that are harder than quartz in here. But for the most part, quartz is the hardest mineral you're going to see. It can have many different colors, but they're often light in color. Not always, but often. It weathers very slowly. So its breakdown at Earth's surface is very slow because it is a network of silicate tetrahedra here with no other atoms mixed in there. So all it has is strong bonds. And it's felsic. It's got no magnesium or iron. So let's see if you can synthesize some of this information and think about why most beaches would be made of quartz sand. What properties of quartz make it so that beaches are made largely of particles of quartz? Think about that for a moment. We'll start with what quartz is made of. Quartz, SiO2, it's made of these elements, silicon and oxygen. We've got a lot of them at Earth's surface. So we've got lots of stuff that would make quartz, at least to start, in the rocks that we're going to start with. Beaches, they're sediments, which means that they're made of broken down other rocks, rock bits. So to get the sandy beaches, we got to take a rock, we've got to break it down, and we remove, by breaking it down, by weathering it, removes other minerals. First, it removes the mafic minerals. Second, it removes the feldspars and micas that are still pretty resistant to weathering, but they're not quite as resistant as quartz. And third, only the quartz is left over because it has not weathered. Because its bonds are so strong, it's resistant to weathering. And as a result, the processing, the weathering that goes on at Earth's surface, producing particles of sand is going to leave quartz left over. So that's the start of learning about minerals. You'll see a lot more about them in lab and also over the course of learning about the 3 different types of rocks. But so far, you're in a good spot if you've gotten this far into the class. So hope you got something out of it. I will see you folks next time.